Welcome to the new era of video creation with Baozi. This is our new series on teaching deep learning. Today, we will discuss the representation learning. Here are the contents. Representation learning is the concept of training a machine learning model to automatically extract useful features or representations from raw data, often without human intervention or extensive pre-processing. In computer vision, the goal is to allow models to learn patterns, structures, and relationships directly from images, rather than relying on handcrafted features. Historically, computer vision relied heavily on manually designed features like edges, corners, or textures for tasks like image classification or object detection. However, this approach had limitations, especially when dealing with high-dimensional data or more complex tasks. Representation learning addresses this limitation by enabling models to learn representations of data in a way that is abstract and hierarchical. Through this, models are able to capture not only low-level features, e.g., edges or colors, but also higher-level abstractions, e.g., faces or objects. In this lecture, we will explore how deep learning, unsupervised learning, and transfer learning contribute to representation learning in computer vision and discuss their implications and applications. The importance of representation learning lies in its ability to overcome the challenges posed by manual feature engineering. In traditional computer vision methods, engineers needed to design complex algorithms to detect and extract meaningful features from images. While some features worked well in specific tasks, they often failed when images became more varied or complex. With representation learning, the model itself automatically learns the relevant features, leading to a more efficient and scalable process. Additionally, manual feature engineering is prone to human bias as it is influenced by the designer's understanding of the task. Representation learning removes this bias, allowing the model to learn features that are best suited for the task. This leads to better generalization, particularly when applied to unseen or new types of data. Furthermore, deep learning models, especially convolutional neural networks, CNNs, excel at learning hierarchical features. Early layers might detect simple edges, and deeper layers might learn high-level patterns, such as shapes or objects, which improves the model's overall ability to understand and classify images in complex scenarios. Deep learning, particularly through architectures like convolutional neural networks, CNNs, plays a fundamental role in representation learning for computer vision. CNNs are designed to work efficiently with image data by learning hierarchical representations. Early layers in a CNN typically capture low-level features like edges and textures. As we move deeper into the network, the model learns increasingly abstract and complex features like patterns, shapes, and even objects. A key advantage of CNNs is their ability to learn spatially invariant features. This means that CNNs can detect features in different locations of an image, making them highly robust to changes in position, scale, or orientation. The model doesn't need to be explicitly told where an object is located within an image, because the convolutional layers will extract relevant features from across the image. Furthermore, activation functions like rectified linear units, ReLU, introduce nonlinearities into the model, which helps it learn complex patterns. Without these nonlinear transformations, the model would be limited to learning only linear patterns. Unsupervised representation learning is a powerful paradigm that enables models to learn from unlabeled data, which is often abundant. Unlike supervised learning, which relies on labeled data, e.g., classifying images into categories, unsupervised learning focuses on identifying hidden patterns and structures within the data itself. Common methods of unsupervised representation learning include autoencoders, clustering, and self-supervised learning. Autoencoders, for example, are neural networks that learn to compress data into a lower dimensional representation and then reconstruct it back to its original form. The encoder part of the network maps the input data to a compact latent space, and the decoder reconstructs the input from this space. The compressed representation captures the most salient features of the data, thus learning an efficient representation. Another important technique is clustering, where algorithms like k-means aim to group similar data points together, based on their inherent features. Self-supervised learning, a more recent advancement, generates pseudo-labels for unlabeled data by creating tasks that require learning a representation. This can involve tasks like predicting missing parts of an image or determining the order of shuffled video frames. Unsupervised methods are especially useful when labeled data is limited or expensive to acquire, and they enable the model to discover useful representations without human intervention. Supervised representation learning refers to training models on labeled data to perform specific tasks, such as image classification, object detection, or facial recognition. In supervised learning, the model is provided with both input data, e.g. images, and corresponding labels, e.g. object categories, and it learns to map inputs to the correct output. Convolutional neural networks, CNNs, are especially effective in supervised learning tasks due to their ability to learn relevant image features through convolutional layers. As the network trains, it learns to focus on the most important features for the task, gradually building hierarchical representations that enable it to perform tasks like distinguishing between different objects or recognizing faces. The key advantage of supervised learning is that the representations learned by the model are tailored to the specific task. The model directly optimizes its learned representations to improve performance on downstream tasks, which leads to high accuracy in tasks like image classification. However, supervised learning requires a large amount of labeled data, which can be a significant limitation in some domains. Transfer learning is a technique that has significantly accelerated advancements in computer vision. It involves taking a model that has been pre-trained on a large dataset, such as ImageNet, and fine-tuning it for a new, often smaller, task-specific dataset. The idea behind transfer learning is that models pre-trained on large datasets have already learned general features, like edges, textures, and simple shapes, that are applicable across many different tasks. Once the model is fine-tuned on the new dataset, it can specialize in recognizing specific patterns related to the new task. This approach not only saves time, but also improves the performance of models in cases where labeled data is scarce. Transfer learning has become particularly valuable in scenarios where collecting large labeled datasets is expensive or impractical. By reusing knowledge learned from one domain, models can perform well in a new domain with fewer labeled examples. Autoencoders are a key tool in unsupervised representation learning. An autoencoder is a neural network that learns to compress, encode input data into a smaller, more compact representation, and then reconstruct, decode it back to its original form. The encoder network maps the input data to a latent space, and the decoder attempts to reconstruct the original data from this compressed representation. The primary goal of autoencoders is to learn a low-dimensional representation that captures the most salient features of the input. These representations are valuable in tasks like dimensionality reduction, where large datasets need to be compressed into smaller, more manageable representations without losing important information. Autoencoders are also used in anomaly detection because they learn to reconstruct data they have seen during training. Data that differs significantly from the training set will not be reconstructed well, making it easy to identify outliers. Self-supervised learning is a powerful paradigm that enables the model to learn useful representations without relying on explicit labels. In this approach, the model generates its own labels from the data by solving tasks, often referred to as pretext tasks. For instance, one common pretext task is predicting missing parts of an image, where the model learns to infer the missing regions based on the surrounding context. Another example involves predicting the next frame in a video or the order of shuffled image patches. By solving these pretext tasks, the model learns representations that are meaningful and transferable to downstream tasks like classification or segmentation. The advantage of self-supervised learning is that it leverages large amounts of unlabeled data to learn useful features, making it highly beneficial in domains where labeled data is sparse or expensive to obtain. This technique has seen impressive success in improving the performance of models, especially in natural language processing and computer vision tasks. Contrastive learning is a form of self-supervised learning where the model learns to distinguish between similar and dissimilar pairs of data points. The objective is to bring similar data points closer in the feature space positive pairs, while pushing dissimilar data points further apart, negative pairs. This contrastive approach allows the model to learn a representation that captures meaningful relationships between data points. One popular example of contrastive learning is SimCLR, which uses data augmentation to create positive pairs from the same image. By training the model to recognize these augmented versions of the same image as similar, it learns to capture essential features of the image. MoCo, momentum contrast, is another method that improves contrastive learning by maintaining a dynamic memory bank of negative samples, allowing the model to train with a larger number of negative examples, thus improving the learned representations. Generative models such as variational autoencoders, VAEs, and generative adversarial networks, GANs, are powerful tools for representation learning. These models aim to learn a latent space that captures the underlying structure of the data. VAEs, for example, model the data distribution probabilistically and learn to map input data to a probabilistic latent space. The decoder then reconstructs data from this latent representation, enabling the model to generate new data samples. GANs take a different approach, involving two networks: the generator, which creates synthetic data, and the discriminator, which distinguishes real from fake data. Through adversarial training, the generator learns to create increasingly realistic data. These generative models are valuable for learning structured and meaningful representations of data that can be used in tasks such as image synthesis, data augmentation, and anomaly detection. By learning the underlying distribution of the data, they can generate realistic samples that resemble the original data. Representation learning also plays a crucial role in cross-domain transfer, where models trained on one domain can be adapted to perform well on another, often with limited labeled data. This is particularly useful when there's a mismatch between the source and target domains, such as when transferring from one set of images, e.g., natural images, to another, e.g., medical images. Domain adaptation techniques adjust the learned representations so that they generalize well to the target domain. One common approach is to fine-tune pre-trained models on target domain data, allowing them to adapt their learned representations. This cross-domain transfer has significant applications, especially in fields like facial recognition, where models trained on one dataset can be adapted to work on different sets of faces, or scene classification, where the model can learn to classify different types of scenes effectively. Evaluating the quality of learned representations is a critical step in ensuring that the model has captured meaningful features. One common way to evaluate representations is by using them in downstream tasks such as image classification, object detection, or image segmentation. The quality of the representations can be measured by how well they perform on these tasks, with metrics like accuracy, precision, recall, and F1 score serving as standard evaluation criteria. Another important evaluation criterion is transferability, which measures how well the learned representation generalizes to new, unseen tasks. A good representation should be versatile and able to perform well across different applications, even if they weren't part of the original training process. For instance, a representation learned from natural images might still perform well when fine-tuned for a medical imaging task. Thus, evaluating representation quality often involves assessing both task-specific performance and generalizability to new tasks or domains.